Today's lesson is going to be remote. I'll be back in tomorrow. But basically, we're just going to look at 3 examples where you make a tree. And if you read up here in the box, it says that we're going to list out all the probabilities of any event and multiply down the path of the tree to get the probability of any one event occurring. So in our example, it says that you're unpacking boxes. You can go ahead and read through it yourself. But essentially, you have boxes, you're reaching in and getting something to drink out of. So in the first box, you randomly pick from 2. So if I start my tree off with box 1, box 2, I have a probability of 1/2 or 1 out of 2. Then you reach in the box and you pick out a cup. In the first box, there's 2 teacups and 3 mugs. So I will show that in my table. And since there's 2 teacups and 3 mugs, that's 5 total, and the total is always our denominator. Lastly, it states that the second box has 1 teacup, 2 mugs, and a dinner glass. So by keeping track of the teacup, mugs, and dinner glass, I have 1, 2, and 1, which is a total of 4 types of cups. The probability of each, like let's say we did box 1 and get a teacup, would be just 1/2 for box 1 times 2/5 for the teacup. And we would get 2/10 or 1/5. Multiplying down every branch to each leaf would give you the probability of any one event occurring, like this. So as you can see, I'm just taking the first box's probability and then each individual cup's probability, multiplying them together, and I get all the probabilities. Lastly, it asks us to find the probability that you'll be drinking from a teacup, so we would just take any probability that had a teacup in it, which would be 1/5 or 1/8, depending upon if you're in box 1 or box 2. And we've seen this a lot where or means add. So we've got 1/5 plus the 1/8. If I make common denominators, I can multiply this one by 8 over 8 and 5 out of 5, which gives me 8 out of 40 plus 5 out of 40, or 13 out of 40 probability of getting a teacup. As you read through problem 2, I won't use up a whole lot of time to explain this, but rather I'm going to use color coding to explain the complexity of all the things that you're going to do. It says that you're going to randomly pick between one of 2 boxes, then you're going to pick an urn, and then a ball out of the urn. So first I'll start with my boxes, and I'll stick with the green and the red for those boxes, but after that we can kind of use colors to indicate what ball or urn we're in, and I'll probably abbreviate as I go through. I won't be picky with how you label your tree, just make sure that it's clear what you're trying to label. So it starts with talking about the urns are labeled A, B, C for box 1 and D, E for box 2, followed by the colors of the balls that are in each of the urns. Just read carefully and make sure your tree looks like this. Before we get too far, let's make sure we put the probabilities for each one. So obviously if there's 2 boxes, I have a 1 in 2 chance of getting into the first box and the second box equally. Since there are 3 urns, there's a 1/3 chance of picking each, 3 being the total. Over here we're back to a half because there's only 2. Now it says that urn A has 2 red, 1 white ball. Now I tried to be as color coded as I could, but a white marker doesn't really show up, so I used black. But you can see I've labeled the numbers. Since there's 3 total, that would be a 1/3 chance of getting white and a 2/3 chance of getting red. Do the same for all the balls in each of the urns. As you can see, all the totals for the balls are my numerators, and all of the denominators are the totals in each urn. Now to find the total probabilities, I would multiply down the list. Now, as you notice, there is a box, an urn, and a ball, so there should be 3 fractions I multiply together. For instance, if I were to go box 1 and go urn A and do a red ball, that would be 1/2 times 1/3 by 2/3. When I multiply straight across, I get 1 times 1 times 2, which is 2, and 2 times 3, which is 18. I would reduce this then by dividing top and bottom by 2 and getting 1/9. I'm not going to show the work on every single one of these. Just make sure you're following the line straight down to wherever you're trying to get to, and multiplying and reducing your answer. Here's what you get. As you can see, I have all of the total probabilities circled, and we talked about this in class the other day, how the sum of all the leaves should add up to 100, and if you add together all these fractions, they do end up adding up to 1 or 100%. Just a way to check your answer. Lastly, to answer the question, the probability that a white ball is drawn, that would be any probability, let's use a slightly different color here, from the white, so that would be 1/18th, 1/24th, 1/9th, 1/16th, and 1/20th. And we have quite a few denominators here that don't match. So you've got a couple options. One, you can put it all into your calculator. Just use the division bar as your fraction bar. Or to come up with common denominators of this many numbers, you would need to find the least common multiple of all the digits. So that means you'd have to count by 18, count by 24, count by 9, count by 16, and count by 20. And whichever number you land on that's in each list, that's the number you'd want to use. I know that sounds long. So for now, let's just use our calculator, but I'll give you a little bit more to work with when I get back to class. Your final answer is 77 out of 240, or about 0.32083, which typically will go out to, I don't know, let's say just to the first two digits. It's about 32%. So either answer, and like I said, we'll talk more about multiple denominators when I get back. For our last one, I think you kind of get the idea of, how to label the weighted branches, not leaves, branches, and multiply on your way down to the leaves. So I'm just going to kind of show you this one, and you can use it in your notes. After this one, I want you to go ahead and start day one. If you don't get it done, you know the drill. It's okay. You're going to have questions, opportunity to ask questions tomorrow, and it's not due until the end of the week. Here's number 3. So our first roll could go one of two ways. It could either be a small number, 1 or a 2, or it could be a 3, 4, 5, or a 6. So it seems like it should just be roll 1 or roll 2, but the way we get roll 2 is predicated on what we roll for the first. So this is the breakdown of the first set of branches. Let's go ahead and label this a small roll, because when we get to roll 2, it says that we need to know whether or not the result is a 1 or not, whereas if we don't get a small number, then the second one we note whether it's a small or not. So here's what that would look like. Let's say we roll a small one first, meaning the next time round we're looking at if it's a 1 or not. Seems like we would put 6 branches here, but really, since we only have to come up with 1 or not a 1, that's just a dichotomy of two scenarios, where it's 1/6 chance of getting a 1 and a 5/6 chance rolling a 2, 3, 4, 5, or 6 to get not a 1. And if we rolled a big number the first time, it says to note whether it is either small or not. So we would say small, and remember again, this was either a 1 or a 2. That's what they qualified as small. So there's again a 2/6 chance of this, or not small, of which case there is a 4/6 chance. Very similar to our roll 1 branches. Multiply all the way through, and each probability ends up being 1/18th, 5/18ths, 2/9ths, and 4/9ths. And I know these denominators are also different and kind of hard to add together to see if the leaves equal 1. So I'll show you another way that we can kind of check this. If you notice at the very beginning, we had a 2/6 chance of anything on this side occurring, right? And if you add together these two, we get 6/18ths, which is 1/3, as is 2 out of 6. So if those match, you're doing good. And then over here, we had a 4/6 chance of anything on this side occurring. And if I add these together, I get 6/9ths, which again reduces to 2/3, as does 4/6. Just another way to kind of check your work. Whoops, I accidentally wrote 6 there. Should be a 3. Also, don't forget that it says down here that there are only 4 outcomes, and that would either be small, small, and then a 1, or small, not 1. And then over here we could say not small, and then on the second one we get a small, or not small, not small again. So really do look at the problem and all the wordings and see if it has anything that kind of gives you a hint as to what the tree should look like. Sometimes that is part of the battle. We said at the beginning that this could have been easily 6 branches per root or per branch, because when you think rolling a dice, you think 1 out of 6. So read carefully, try your best on day 1, and I'll see you guys tomorrow. Thanks.